So digitized collections, they're a big thing. They're currently ongoing, not just in sort of national resources like iDigBio, which is the integrated digitized biocollections, but also in individual institutions like the Natural History Museum, where it makes up a key part of their strategy. And this is not just for the preservation of the specimens, but also to get these sort of, in the Natural History Museum at least, these sort of 80 million specimens out of the drawers and into the public domain. So now we've got these specimens digitized, how can we use them? Are they just going to be sort of sitting in databases? There are some automated programs that use forearm identification or leaf character identification, but we'll be looking at brachiopods. So brachiopods are pretty awesome, they're useful, and luckily we've got a lot of them. In the NHM alone, there's about 1,000 drawers of Mesozoic and Cenozoic brachiopods, which makes up about 400,000 specimens. And this is just orders of magnitude more than have been published on. And at this rate, will ever be published on. Because, as you're all aware, there's sort of that time and labor-intensive factor of doing research. So this study uses 1,200 specimens of a well-documented PhD study from the Palaeontological, that's early Jurassic, Spain. So here are the 11 taxa I used, pterobrachioids on the left, rhynchonelids on the right. So our key questions. So how precise are measurements made from traditional approaches, which is to say calipers? And can you collect better data, or data that's, can you collect data quicker or more efficiently from specimens images of specimens produced by digitalization? So basically, can we get through all of these brachiopods or other specimens that we have? So what do I mean by better data? For this study, we looked at precision. So basically, for each specimen, we took 6 measurements, and that's 2 of length, 2 of width, and 2 of depth. So for calipers, that's fairly self-explanatory. You just took 2 measurements of each measurement, either one person taking 2 or 2 people each taking measurements. For our automated data, that was slightly more complex in that we took 3 photos of 3 orientations of each brachiopod. So dorsal, lateral, and posterior view. And from these, you can see you can get 2 lengths, 2 widths, and 2 depths. And from that, from the 2 measurements, we looked at precision. So this is the easiest equation you've seen in the last few days. And so basically, precision is an important thing, but it's not actually known very much because, for obvious reasons, not many studies take 2 measurements. So starting off with calipers. And the taxa, you can see color-coded here, and that remains the same for all of the rest of the talk. And the rhynchonelids are the warm colors, pterobrachioids are the cool colors. So for calipers, and this is within person precision, so just one person taking 2 measurements. And you can see that calipers are ubiquitous, at least at this scale, and that's for fairly good reason. We've got, for length and width, there's under 1% difference, very high precision. For depth, because of some slightly interesting shaped brachiopods, you can see these four ones here do drag up the mean. So, however, interperson differences do exist. So for width, roughly the same results. 2 people both consistently got more or less exactly the same results. For length and depth, however, that's not so much the case. You can see here these positive values mean that one person consistently measured their brachiopods bigger, whereas in depth they consistently measured them smaller. So how come that happened? Basically, training problems. These 4 brachiopods were not quite the same shape as what they were the example taxa, and people got confused. So this is obviously not a problem if people know what they're doing, but when you're studying and you're sort of handing off your measuring to your untrained students, problems can occur. And when it's sort of averages of the differences are sort of 7%, that's not great. Yeah. So when you divide them up, take away the problematic taxa, you can see that these differences go back to sort of around 1%, so it's 1-2%, so that's better, but still, you don't really want to be not knowing whether this is happening in your data or not. So here are the 4 problematic taxa with these ones are the problematic ones. This is Lobothyris, which is sort of the example basic shape. And you can see here the interesting sort of shapes that sort of, yeah. But basically they are brachiopods, they're simple organisms. If you're measuring something more complex, then how much more wrong can it go? It's also bringing up to the next part of the talk. Man versus machine. Can machines do this better? So automated data collection, the second part of the talk. So you can see here, right off from the bat, there's a problem with our automated data collection, which is someone actually has to position the brachiopods and take the photos. And this introduces the manual human error right from the start. So this one's Chris, and you can see the camera up here. We're positioning the brachiopods in a box of sand with a black cloth over the top. So that allows us to orientate them in the different orientations. And here's the photo that comes with the scale bar, the reference cards, and reference for the algorithm to, I'm not entirely sure about how this technical stuff works. So here's the Brachiomatic, which I didn't name. I'll say that up front. So that sort of it goes through this technical magic, and we get this output. So you can see there are some errors here in the beginning. This one here, this is an algorithm error where it's not actually the brachiopod, it's the algorithm didn't accurately detect the shape of the brachiopod, so it took a chunk out of it. And this is sort of one of the main algorithm issues, other ones where it just didn't detect the brachiopod at all for whatever reason, or it took chunks out of it, it registered the background as brachiopod. So those are the algorithm issues. The manual issues involve the brachiopods. Because of the different orientations, they're sometimes standing on end, standing on their side, and they would just tilt over. Sometimes they fell over completely. Sometimes they'd be rotated to one side. So those are the manual issues in the process. So what did we measure? So we measured, in order to compare the data directly to the caliper measurements, we looked at these red lines, which are the most distant measurements on the X and Y axis. And those are quite susceptible for the brachiopod being tilted over, though there are lots of other variables which we could have looked at, and we possibly will still look at in the future. So how precise was it? And we had to conclude it wasn't actually very precise at all. So you can see here that the mean's almost 8% for the depth. That's twice as much as for the calipers. These ones, 3.4, 3.5%, over three times worse than the caliper precision. And also, even in some of these extreme cases, 60% difference is not great. So basically, the fact that it's depth, for the calipers, there was a fairly sort of consistent, it was the taxa that was making the data skewed. For this one, it's actually the taxa are fairly consistent, but the depth is one that's the biggest problem. And that suggests that it's not the algorithm it's creating the problem, it's the fact that the depth is created from the the lateral and the posterior views, and those are the ones which are most likely to fall over. So it's a handling issue, basically. Again, to highlight this handling issue, the fact that smaller brachiopods are less precise by quite a margin. So when you've got a small brachiopod, it's fiddly, you're trying to position it, it's more likely to do something you don't want it to do. So out of interest, looking at the trends through time, despite these differences, we did actually get very similar results. We both got a significant decrease from the Pliensbachian to Toarcian. So, yep, despite the differences, that's the same. So we come to our conclusions. So basically, there are differences in precision between taxa and also between the measurements. And this has implications for when you're using calipers for existing studies. If you're using untrained students, are these students going to not quite know what they're doing? And also implications to when you're using algorithms and automated data, and also when you're sort of collecting data through the digitized collections. So is this, you need to make sure that you're basically not sacrificing quality for quantity. Second point, measurements from digitized images have the same problems. Yeah. So basically, you'd think you'd be able to get away with, from moving from calipers to automated systems, you'd be able to get away with all of this human error. But in fact, it actually gets worse. There's more human error and manual handle issues associated with the algorithms than with using calipers. However, that said, automated systems, digitized collections are still a new technology, and they're only going to be getting better with time, sort of better algorithms, better ways to position your specimens. And also it's true that brachiopods are slightly fiddly. If you're using something like butterflies, there's sort of much easier to measure size from a butterfly or a dragonfly, that sort of thing. So also, the automated systems are reproducible. So once you've got the images, you can share them as many times as you want. Once you've got your algorithm, you can share it around. You can't do that with specimens. There's just no way of doing that. So in the future, you could say that while calipers are currently better for the way we did it, calipers, you're not going to be reinventing the wheel anytime soon. You can obviously get people who are better at calipers than others, but it's going to be more or less the same. With the algorithm, it's only going to be getting better, maintaining the benefits while decreasing our problems. So, yep, and overall trends through time are similar. Thank you. So, thank you for listening.